Hello, in this session I'm going to look at probability 3. Now, a tree has branches, and that's exactly what we're going to use in this example. So we'll start with a coin with a head or a tail. When we toss, and we're going to toss this coin 3 times. So when we toss this coin 3 times, each time that we toss, we can either get a head or a tail. I'm interested in 2 cases. One, when I get all tails. So that means that I toss it 3 times and I get 3 tails in the 3 tosses. The other case is when I get 1 tail only. So this means that I toss it 3 times, so maybe I'll get a tail in the first time and head in the next 2 times, or I might get a tail in the second time but head in the first time and the last time. Well, you can see that it's getting a bit more complicated now, because in each of this case, or at least in the second case, there are a few possibilities. Okay, so the way to do this particular question, or one way to do this question, is to use a probability tree. So this is what it looks like. I'll start from here. Alright, just start from a point and draw 2 lines. So there's nothing there in the beginning. Now the 2 lines here represents 2 possible outcomes when I toss the coin once. So this is the toss, the first toss. Okay, in the first toss, I can have either a head or a tail. Now in the second toss, if I get a head in the first toss and then I toss it a second time, I can get either a head or a tail again. Alright, if I get a tail on the first toss, then when I toss it the second time, I can also get either a head or a tail. Right, and now if I toss that the third time, So if I get a head on the second toss, I can have a head or a tail on the third toss. If I got a tail on the second toss, I can also get a head or a tail in the third toss. Alright. So you can see that we have more and more branches. One branch branches out into two, and each of those branches out some more. So it looks like a tree. That's what happens in a tree. Branches keep branching into more and more branches. And what we have here actually is a picture that shows all the possible outcomes. Well, you can see that it would get more and more complicated if I have more and more tosses. Alright, but in this case it is okay. We have 3 tosses and this is all we are looking at. Alright, we have everything here. Having sketched out all the possible cases, let's try and do this question now. We are interested in the probability of getting all tails. So let's look at this tree. All tails means that when I toss the first time, I get a tail. I get this one. Okay. When I toss it the second time, I can get a head or a tail, so I'm interested in getting a tail again. And in the third time, I want to get a tail as well. So I'm interested in this particular chain of event. Tail, tail, and tail. So from the tree, I can pick out the particular set of events that I'm interested in. And the next thing we could do is that on each branch, write down the probability of that branch. For example, if I look at this branch is about the getting a head when you toss it. And the probability of getting a head is half. The probability of getting a tail is also half. And you can see that for each of these branch, the probability is always half because it's just tossing the same coin. So let's follow the events that we want. Getting all tails. So the next branch that gives a tail also has a probability of half, and the next one also half. I have these 3 probabilities. Alright. Now, if I now want to find the probability of getting all tails, what can I do? The way to do it with a probability tree is to follow the chain of events that you want, in this case tail, tail and tail. Follow those branches and multiply the probabilities on those branches. So in this case it would be half times half times half. And that's the answer. 1/8. right? That's the answer for the probability that all are tails. Next, we look at the probability that we have one tail only. That's a bit more complicated. Let's try and pick out some cases. We have followed this branch just now, and in this case we had all tails. We had 3 tails rather than 1. So what we need to do now is we need to pick out those series of branches that has only 1 tail. So let's start from the top. If I follow this line, I will get all heads, so that's not what I want. But if I follow this to here, head, and tail, that gives me 1 tail. Right, so in fact I can mark out this particular chain of events by, say, putting a tick there. Alright, if I put a tick next to this T, this tail here, then I know that I'm referring to, if you backtrack along the branches, there's only one way to backtrack. Whereas if you go forward, it keeps branching to more and more possibility. But if you go right to the last event, the outcome of the third toss, and you work backwards, there's only one way to do it. So that's a good way to keep track of a particular chain of events. So we can have head or tail, or head and tail, and this is one possibility of getting a tail only. Now let's look at another one. If we follow this, right, let's do it backwards, of course, that's the idea, isn't it? So let's go down to the next one. Head, tail, head. It's 1 tail here, just the 1 tail. The next one, tail, tail, head, 2 tails. Don't want that. Next one, head, tail. Right, that's 1. And then we have tail, head, tail, 2 tails, not good. And then head, tail, 2 tails, tail, 3 tails. So quite easily we have picked out these 3 cases, 1, 2 and 3, that each of them has just 1 tail. So these are the chain of events that we are interested in. Now I want to find the probability of having 1 tail only. But we find that there are 3 possible events, or 3 possible chains of events that can give us 1 tail only. Let me write all of them down. So this is when I have head, and tail. Alright, so I can have head, tail, head, tail, that's 1 possible series. I can have this one, head, tail, head. That's another one. And I can have that one, tail, head, head. That's yet another one. Now to calculate the probability of one tail only, we can calculate the separate probability of each of these cases and add them. If you remember from the last session, I talked about the addition law of probability. You might remember that we can add two probabilities if the events for those with those probabilities are independent. That means that one event does not affect the other events at all. That was not right. Let me say that again. We can add two probabilities when the events for those probabilities are mutually exclusive. Alright, that's different from independent. Independent events can happen at the same time. They just don't affect one another. But mutually exclusive events are different. They do affect each other in the sense that if one event happens, the other must not happen. So that's a very big effect. So when two events are mutually exclusive, meaning that if one happens, the other cannot happen. If they are mutually exclusive, then we can add the probabilities. What we need to check here is whether those three events are mutually exclusive, meaning that if I get this, does it mean that I cannot get that? So if I get a head-head-tail, does it mean that I definitely cannot get a head-tail-head? Let's look at this. If I get a head-head-tail, it means that we are looking at this. It means that the first toss, we get a head, second toss head, third toss tail. Alright, so I've done the three tosses and I get a head-head-tail. That's what head-head-tail means. Now what does it mean by head-tail-head? Head-tail-head means this one. Head-tail-head, it means that my first toss is head, second toss is tail, third toss is head. So I've done the three tosses and I get a head-tail-head. Now you can see that they have to be mutually exclusive because in each case I've already finished the three tosses and I get this result. So if I've already got head-head-tail, I cannot also have gotten head-tail-head. Alright, and if I've gotten head-tail-head, then I have not got head-head-tail. They're obviously either one or the other. Alright, it's just like this thing has already happened, so it cannot be that something else have happened at the same time to the same die. So they are mutually exclusive, and therefore I can add the probabilities of these three cases. So let me put a P next to it to say that I now want to think of the probabilities. P with a bracket and a P with a bracket, and I want to add all of them to get the answer. So in the next step, I need to calculate the probability of head-head-tail. So let's go to that chain of events. That would be this one. head, head, tail, we can, as we follow these branches, write down the probability for each branch. So this will be half, because this branch means that after the first toss, I toss it again a second time and I get a head. So the probability of this branch is only for that toss, that second toss itself. And when I do the second toss, it's equally likely to get a head or a tail. So the probability of getting a head is half. And after that, when I toss that again, I want to know the probability of getting a tail when I do the third toss. Alright, so again, that's just a toss, and the probability of getting a tail is also half, just like any other tosses. Okay, so now I have the probabilities along all the branches along this chain, and it is half, half, and half. And if you remember from the first example, the way to calculate the probability of this series of branches, a particular series of branches, is simply to multiply them. So it's half times half times half. And we know that the answer is 1/8. In the next case, head, tail, head, that would be this one. Head, tail, head. Now you can see that because they are all tosses of the same coin, all branches would have a probability of half. And because of this, it's always half times half times half, and we will get 1/8 again. And in the same way for the last case. So we have the answer now. It's 1/8 plus 1/8 plus 1/8, 3/8. So in this way, we have found the answer to both questions of getting all tails or just one tail only. And this is how we use a probability tree. But one thing I should mention here is that the reason for multiplying the halves in the first example. So let me just go back to the first example, the probability of getting all tails. Now, that was for this particular series of branches, tail, tail, and tail. So I said that to find the probability of getting tail, tail, and tail, I would multiply the probabilities for each of these events. Now, if you remember from the last session, I talked about how you can multiply probabilities for two events when the events are independent. And independent means that one event has no effects on another event. So that means that when one event happens, it does not affect how likely the other event is going to happen at all. And that's what we mean by independence. And that when two events are independent, you can actually multiply them. Now in this case, we have to be a little bit careful here. I've said that you can multiply the probabilities when you follow these branches. Now the reason why we can multiply the probability in this case is actually not because these events are independent. Now it might be a little difficult to understand here, because obviously you might think that you would think that these events are independent. Alright? When I toss the tail a second time with the coin, it shouldn't depend on the first toss. And that is true. Alright, that is true. And in that sense, we can also say that we multiply them because they are independent. Right? And it's fine to use that reason for this particular example. What I mean is that in other examples, it is possible that the second event depends on the first event. For example, you can imagine a problem where we have balls of different colors in a box. Alright, and that each of these events is about picking out a ball to see what is the color. So the color is the event. Now, if it is about picking balls from a box, then clearly picking the ball once, and if you don't put it back, will affect the answer for the second ball that you pick, will affect the probability for the second ball that you pick, because you have fewer balls in the box after picking the first one. And the probability, you have the corresponding probabilities along the branches, and you'll find that the second time you pick a ball, the outcome is affected by the first time you pick a ball. But in that example, even though the second probability is affected by the first, you can still multiply the probabilities in order to calculate the answer along a certain chain. So what I'm saying is that when we do a probability tree, you can always multiply the probabilities along a certain chain of branches, even if the events of the next branch is not really independent of the event in the event before that. And that's a special case of probability, and we shall not go into that for O level, for this particular level of maths. But I'll just mention that this is a rather subtle example in which even when the second event depends on the first, you can still multiply them, because you will come across such examples like picking colored balls from boxes. So it's good to know that the reason for multiplying this is not because they are independent, but it's because you're doing a probability tree, and for a reason that we will not go into, you're still allowed to, or rather you can still find the answer by simply multiplying the probabilities one branch after the next. Okay, so we'll stop here for this session. See you next time.